Okay, we're going to deal with velocity and acceleration in 3D. Um, the vector velocity is a function of t, and it is simply defined as the first derivative of the position. This is the position vector. The acceleration, again, is, again, a function of t, and it is defined as the second derivative of the position vector. Another way to think of this is that the acceleration is the derivative of the velocity. So this is a standard definition. Um, let's do a quick example. Example 1, r of t will be a two-dimensional vector t squared, which is simply a regular parabola. Let's say t is positive. So we just have a irregular parabola. So the velocity vector v is going to be r prime, which in this case would be 1 to t. So if you are at 3, 9, so that is the position, 3, 9, which means that t is equal to 3. Then we have a velocity, which is, in this case, when t is equal to 3, we would have that the velocity is 1, 6, because t is 3. So 1, 6 would be a vector 1 and 6 units up. This is not proportionally correct, but it is 1, 6. So this would be the vector 1, 6, starting from this point, 1 forward, 6 up. All right, the acceleration is going to be the second derivative, which is going to be 0, 2. So the acceleration is going to be this vector up here, going up, which changes the velocity vector as we move on. So the velocity vector is going to be tilted up by 2 units. And this makes sense. Let's say this is going to be a little messy. Let's draw a new picture. Let's say, to make it less messy. So let's say we're at the point 4, 16. Yep. So what is the velocity vector? It's going to be much steeper at that point. The velocity vector will be, remember, the velocity is 1 double t. Here, t is equal to 4. Double t would be 8. So the velocity vector would be 1, 8, which, when you think about it, is the same as the vector 1, 6 added to 1 to 0, 2. So if we change this by adding 0, 2, we end up with 1, 8 from 1, 6, which implies that the acceleration vector changes the velocity vector. This problem, this particular example worked out really well, but not all of the examples are that easy that you can just add a vector and get at the next one, because this is a continuous change. Yeah, we don't have a discrete change where you just add 0 to every time. This particular problem just worked out nicely, but many of the problems are not as easy. One thing that we want to, so this is the end of example 1. One thing we want to concern ourselves with is, okay, which way is the acceleration going? Is it going up, down, relative to the curve? So if you have a curve, you have your tangent unit vector, your normal unit vector, and the question is, how is the acceleration behaving relative to those? It turns out that the acceleration will always, always, always be, no matter where in space, a combination of those two. By combination, we mean one of them could be 0, but nonetheless a combination, which has an implication. The acceleration, so let's say this is the acceleration, will be on the same plane as t and n, which is very interesting, I think, because the acceleration does not tell you whether you start. So I'm sorry to interrupt myself. Let's say this is on a plane for now. But then this, as we move forward, this is going to either come towards us or go away from us, this curve. Okay, the tangent vector is flat on the oscular. So we're on the oscular plane. Right now what we're drawing is osculating plane from the previous video. But except that here, the curve may be coming towards us or away from us relative to this plane, the Eusklerian plane. The tangent vector is on the Eusklerian plane, the normal vector is on the Eusklerian plane. And what is, in my opinion, amazing is that the acceleration is also on the Eusklerian plane. That is interesting to me because it doesn't tell us anything about whether the graph is going to move towards us or away from us, since we are just using those two vectors, to a combination of those two vectors to come up with this one. The acceleration, by the way, may or may not be unit. It's not necessarily a unit vector. It's just a vector that tells us how the tangent is changing, which makes sense. So at this point, the tangent is changing by this direction. So if the tangent is going like this vector is pulling it this way somewhat. It's pushing it this way. But nonetheless, what I'm trying to say is that it's always on the same plane, although this could be moving up or down. Having said that, though, once we are in a new position, the new point may or may not be on the same plane. So once you move a little bit, a delta x, or rather a delta t, to a new position, then this new position may not be on the same plane anymore. So the position itself is what tells us whether we are moving away from the page, from the Eusklerian plane, or closer from the Eusklerian plane. I mean, away from the Eusklerian plane, either towards us or away from us. That's what I was trying to say. Let's do a quick example. So example 2. And I think you're guessing what kind of example we're going to use. Our friend cosine of t, sine of t, and t over 2 pi, which is a helix. This time we're going to do this in a different place. We're going to find the acceleration at a different point. So let's talk about this for a moment. So we have the three-dimensional space, and we have this coming down this way. So this point is 1, 0, 0. This point here, this one up here is 1, 0, 1, 1 unit up. And this would continue down here. Yeah, I don't want to, it comes all the way back here this way. So this is a helix that goes continuously up, just like our slinky. Where is it? Just like this guy. Actually, it's positioned the other way. There we go. Yep. So it's the same kind of situation. It goes up and down. All right. So this position happens when t is equal to 0. The tangent vector, I'm not going to figure this out. The unit tangent vector, although it doesn't take that long, so I might just as well do it. So the derivative is going to be negative sine of t cosine t, and then 1 over 2 pi. That's the tangent vector, so it's going to go up a little bit. If we plug in 0, r prime of 0, we end up with 0, 1, 1 over 2 pi. So the tangent vector is going to go up. It's going to go to the right from that point, initial point, and then it's going to go to the right and up a little bit, to the right and up. It is not going to go back or forward. That is the tangent vector. This is interesting. The normal vector, but this is not the unit tangent vector. The unit tangent vector is going to be in a different um, yeah, the unit normal vector, we had it from a previous, um, oh, the unit tangent vector first from a previous video is the one that is really complicated, man. It is 2 pi over that root of 4 pi squared plus 1. And it has negative sine, cosine, negative sine t, cosine t, and 1 over 2 pi. Okay. But what I really wanted to show you, so that has the same direction as this guy at that point, but it is shorter, or yeah, it is shorter than this guy. So this is the velocity vector. Um, and then this is the unit tangent vector, not to be confused with the velocity vector. They have the same direction, but different magnitude. The normal vector, on the other hand, is looking at my notes. Yeah, that's the one that is a little easier. Negative cosine t, negative sine t, and 0. So that is the one I want to emphasize. So this vector is, when we plug in 0, we get negative 1, 0, 0. So this is the normal vector pointing that way. And then the tangent vector is going up, is going to the right and up a little bit. So that's the tangent vector and the normal vector. And the acceleration is going to be in between. Oh, it could be in between the two, or it could be behind. What I meant to say by in between is that the acceleration will be on the same plane as those two. And that plane is not a horizontal plane, it has a tilt. So that's what's kind of telling us a little bit about its motion going upward. The tilt itself, which is given by the uh, by the tangent vector, tangent unit vector. Anyway, this is way more complicated. What I'm showing you right now is more complicated than what we have to do. The reason is because we eventually want to link the acceleration with the tangent vector and the normal vector. So we got tangent vector, normal vector. I haven't shown you the acceleration. I'll show you the acceleration right now. And again, this is way more than what we have to know for the acceleration. The acceleration was very easy. I mean, look back at this example. It took 1, 2 steps, plug in the numbers, and then we got the acceleration. Here, it is going to take the same amount of steps. So let's show you. Again, the reason why I'm showing you more is because we want to link the acceleration with the tangent vector and the normal vector. So let's start with this, cosine of t, sine of t, and t over 2 pi. Okay, so the velocity, by the way, we're going to label, yeah, this as v, and the magnitude of the velocity is going to be written as script v. I'm going to go back to that in a moment. Anyway, so this is negative sine of t, cosine of t, and 1 over 2 pi. The acceleration is the second derivative of the motion, which is going to be negative cosine of t, negative sine of t, and 0. So if you want the acceleration at 0, all we have to do is plug in 0 for t, and that's going to give us negative 1, 0, 0. There. If you just wanted the acceleration and nothing else, this is it. This is all you have to do. First derivative, second derivative, plug in the number, you're done. It takes only a couple steps to get the acceleration. Negative 1, 0, 0, which is, by coincidence, this same vector as the normal vector. It's not necessarily always the same. What happens here is that we have a circular motion, and in a circular motion, the acceleration happens to go towards the center. Um, if this was not a circular motion, then we wouldn't necessarily have um, an acceleration towards the center of the circle. But that is what's going on. The circular motion causes the acceleration to go towards the center of the circle. So there we have it. But now it gets much more complicated than that, because we want to link the acceleration. In other words, we want to write the acceleration as uh, some scalar times the tangent vector plus another scalar times the normal vector. By doing this, we achieve two things. The main thing is that the acceleration is on the same plane as the normal vector and the tangent vector. In other words, the acceleration is on the osculating plane of the curve at that given point. That is very crucial. The acceleration does not show the left away from the osculating plane, which I find very interesting. Okay, relative to the osculating plane again. Before we continue, let me record that script v is going to be the magnitude of the velocity, which is the same thing as the magnitude of r prime. Yeah. And remember that r prime is used in the length of the arc, the arc length. So for instance, if you have, if you want to find the length that is equal to an integral of ds, but that is the same thing as, there are some numbers here that we gotta put. And remember, this is the square root of dx dt squared plus dy dt squared. So this is a review, quick review of what we've doing. T squared dt, and let's just label this as from going from A to B. And this happens to be the magnitude of the vector x prime, y prime, z prime, where the primes correspond to t. Same integral, A to B. And that is the same thing as r prime. The consequence of this is that if we do the derivative of s with respect to t, we end up with r prime, which, by the way, r prime is v. This gets really, there's a lot of terms going on. The relationships are few, but there's a lot of terms that we are linking together, and that will happen through the whole semester. There's a lot of terms that are linked together. So we have the velocity combined with r prime. Well, it is the same thing as the magnitude of r prime. And consequently, yeah. The derivative of the length relative to t is the velocity. So that is one thing we have to keep in mind. There's a few things that we have to keep in mind. So the derivative of length with respect to time equals the velocity. Okay. What else do we need to know? Well, the normal vector is equal to the tangent, the derivative of the tangent vector over the magnitude of the tangent vector, which means that the derivative of the tangent vector is equal to the magnitude of t times the normal vector. So if we multiply this equation by the denominator, we end up with that. There's one more link we need before we start putting our formula together. The other part we need is the curvature. The curvature is defined as how much the tangent vector is changing relative to the length of the curve. Now, this is by the chain rule, this is dt over dt over ds over dt. So this is the derivative, is just t prime. And ds dt, as we have explained earlier, is the velocity. Up here, though, t prime, the magnitude of t prime, let me pause for a moment. Okay. So here, looking at this equation, what we have is that the curvature is equal to, I'm just rewriting what I have explained here, is equal to the magnitude of t prime over the velocity, which means that the magnitude of if we multiply both sides of the equation by the velocity, t prime, the magnitude of that is equal to the curvature times the velocity. Now let's go back to this equation. That means that t prime, or this gets kind of convoluted, is equal to the magnitude of t, which we just found out to be kv, times the normal vector. So remember, this is not k, this is the kappa, the curvature, velocity, the normal vector, and that's t prime. The reason why we need that is because, let me draw a line here. Okay, so the velocity is equal to r prime of t the speed is the magnitude of that the tangent unit vector is t is r prime over the magnitude of r prime, so that is r prime over the velocity. And if we multiply this equation by the velocity, we have that r prime is equal to the velocity times t. R double prime, which is the acceleration, is found by using the product rule. So we have v prime t plus v t prime. Okay, so we have written the acceleration in terms of t and something else, but we want to express this in terms of the normal vector. So v prime t plus t prime, on the other hand, back here, is the curvature Vn. So this guy gets substituted by the curvature Vn. So we have that V to start with, times the curvature Vn, and that is V prime t plus curvature V squared n. Okay, so the acceleration can be written as a scalar, which is V prime t plus curvature velocity squared times the normal vector. This part here is called the tangential component of the acceleration. Tangential component of acceleration. And this is labeled as the normal component of acceleration. There is times when I will ask you to find the components, the tangential and the normal components of the acceleration. And probably this is the best way to do it, uh, by using those formulas. So remember too that the curvature can be found by r prime crossed with r double prime over r prime. All of those are magnitudes cubed. Yep. And that is the same thing as the velocity cubed on the denominator. So r prime cross r double prime over velocity cubed. So again, the acceleration, which is a vector, can be written as the velocity, rather the derivative of the speed. I think I have misspoken a couple times. The magnitude of the velocity is the speed. I'm going to rewrite that in a moment. T plus the curvature is this, so we can rewrite this as r prime cross r double prime. We're going to multiply by v squared, but we are dividing by v cubed. This is in magnitude, so we can just divide by v once. And most books probably have this formula. I personally prefer this formula. It is the same thing. Just be aware there's a couple different ways to compute that. What I like about this formula is that there's no need to multiply by v squared, and if we're going to divide by v cubed anyhow. Let's do a quick example. Let's repeat example 2, the one we did here. Yep. Sorry. There it is. In example 2, we finished and we ended up with this answer. But we're going to do the example. Remember, this example was super fast. There it is. That is essentially finding the acceleration. But we're going to find the acceleration differently, assuming that we know t and n. So we're going to redo example 2 in a more complicated way. What we are gaining by doing this is that we are understanding a little better the relationship between the acceleration, the tangent vector, and the normal vector at one particular point. So there's the curve. We know it is r equals cosine t, sine t, and then t over 2 pi. Remember, this point is initially 1, 0, 0. And then we have the tangent vector, which is going to be 0, 1, 0. And then the normal vector at that point, this is happening when t is equal to 0, is negative 1, 0, 0. Yep. So the acceleration, we already saw the acceleration is the same as that. That was again, the reason is because we have a circular motion, and that causes the acceleration to go towards the center. But in a non-circular behavior, then the acceleration will not go towards the center, because what would be the center then? I guess an ellipse would have a center, but anyway, let's find the tangential component of the acceleration. So first we need to know v. In order to find v, we need r prime. So r prime is going to be negative sine of t, cosine of t, 1 over 2 pi. That's v. The velocity is the magnitude of this. I'm sorry, again, I keep, so v by itself is the velocity. Script v, which is the magnitude of the velocity, is the speed there. And the speed is the magnitude, so we're going to take this vector and find its magnitude. Negative sine t squared plus cosine t squared plus 1 over 2 pi squared. And of course, that's going to add up to 1 plus that. We know where this is going. 4 pi squared plus 1 over 2 pi. Okay, so that is the velocity, but that's not the tangential component. We have to find the derivative of it with respect to t. So the derivative of the velocity, which is this number with respect to t, is 0. Just 0. Yeah, because this is a constant, there's no t involved in here. This is a number. It's a number that is a little bigger than 1. So its velocity, its derivative is 0, which means, according to this, that the tangent vector does not contribute to the acceleration. The acceleration is this much of tangent plus this much of normal. Normal goes towards the center, tangent. So there's no contribution in this particular example, in this one. That doesn't happen all the time. Sometimes it goes that way, sometimes it goes that way. It varies. So there's no contribution. What is the contribution of the normal vector towards the acceleration and in this example? So let me copy again. R equals cosine t, sine t, t over 2 pi. R prime equals negative sine t, cosine t, 1 over 2 pi. R double prime is negative cosine t, negative sine t, 0. The cross product, R prime cross R double prime. Well, let's see, it's 0. 1 over 2 pi, and then we multiply those two. Sine of t, comma, 0, negative 1 over 2 pi cosine of t, and then sine squared plus cosine squared 1. We can factor 1 over 2 pi as we have done before. So we have sine of t, negative cosine of t, and 2 pi. Yep. So the magnitude of R prime cross R prime, R double prime, this is a scalar, so we can just factor that out. And then the magnitude of this is sine of t squared plus negative cosine of t squared plus 2 pi squared. So that adds up to 1 plus 4 pi squared. So we end up with 2 pi in the denominator, the square root of 1 plus 4 pi squared. Okay, so that is this product. The velocity, which is what we need to divide by to obtain the normal component of the acceleration. So there's the product, we need to divide by the velocity. Where's the velocity? I'm not sure I found it. I think I did find it earlier. Oh yes, it is right here. It is the velocity is the magnitude. See, I keep saying velocity again. I apologize for saying velocity. The speed is the magnitude of the velocity, which we had found earlier. So it is this number, which happens to coincide with this. Here, it is the same number. So when we divide uh, r prime cross r double prime over magnitude over the velocity, this is nothing, we end up with 1, which means that the contribution of the normal vector to the acceleration is 1. In other words, in this particular case, in this particular example, and for this particular point, the acceleration is nothing, that's a 0, on the tangent plus 1 on the normal. 1. In this particular case, of this particular r equals cosine of t sine t, t over 2 pi, and at a point at t equal to 0. I believe it is the same at any point. The tangential will not matter. Yeah, because the velocity, the velocity is independent of t. We did not plug in t. This came out of the sine squared plus cosine squared regardless of the t. So the velocity, the derivative of the speed relative to the time is going to be 0. So this is always going to be the case that we get no contribution for the tangential vector. I mean, no contribution of the tangential vector for the acceleration. And is this always going to be 1? We did not plug t at all, which means yes. So this is the case. The acceleration is always going towards the center. So here's my slinky. So the center is here, and the acceleration is going always towards the center, even though this is spiral, this is a helix, and it's moving upward or downward, depending on how you're looking at it. The acceleration is always towards the center, which is very, very interesting. So we're going to stop this video here.